Just as Newton had been born the year that Galileo died, so Einstein was born the year that Maxwell died, and he saw it as part of his mission to extend the work of the Scotsman. Here was a theorist who had shed prevailing biases, let mathematical melodies lead him into unknown territories, and found a harmony that was based on the beauty and simplicity of a field theory. At first, the electromagnetic field theory developed by Maxwell seemed compatible with the mechanics of Newton. For example, Maxwell believed that electromagnetic waves, which include visible light, could be explained by classical mechanics, if we assume that the universe is suffused with some unseen gossamer light-bearing ether that serves as the physical substance that undulates and oscillates to propagate the electromagnetic waves, comparable to the role water plays for ocean waves and air plays for sound waves. By the end of the 19th century, however, fissures had begun to develop in the foundations of classical physics. One problem was that scientists, as hard as they tried, could not find any evidence of our motion through this supposed light-propagating ether. The study of radiation, how light and other electromagnetic waves emanate from physical bodies, exposed another problem. Strange things were happening at the borderline where Newtonian theories, which described the mechanics of discrete particles, interacted with field theory, which described all electromagnetic phenomena. Up until then, Einstein had published 5 little-noted papers. They had earned him neither a doctorate nor a teaching job, even at a high school. There was no sign that he was about to unleash an annus mirabilis, the like of which science had not seen since 1666, when Isaac Newton, holed up at his mother's home in rural Woolsthorpe to escape the plague that was devastating Cambridge, developed calculus, an analysis of the light spectrum, and the laws of gravity. But physics was poised to be upended again, and Einstein was poised to be the one to do it. The breakthroughs that he wrought during a 4-month frenzy from March to June 1905 were heralded in what would become one of the most famous personal letters in the history of science. Conrad Habicht, his fellow philosophical frolicker in the Olympia Academy, had just moved away from Bern, which, happily for historians, gave a reason for Einstein to write to him in late May. Dear Habicht, such a solemn air of silence has descended between us that I almost feel as if I am committing a sacrilege when I break it now with some inconsequential babble. So what are you up to, you frozen whale, you smoked, dried, canned piece of soul? Why have you still not sent me your dissertation? Don't you know that I am one of the 1½ fellows who would read it with interest and pleasure, you wretched man? I promise you 4 papers in return. The first deals with radiation and the energy properties of light, and is very revolutionary, as you will see if you send me your work first. The second paper is a determination of the true sizes of atoms. The third proves that bodies on the order of magnitude of 1/1000th millimeter, suspended in liquids, must already perform an observable random motion that is produced by thermal motion. Such movement of suspended bodies has actually been observed by physiologists who call it Brownian molecular motion. The fourth paper is only a rough draft at this point, and is an electrodynamics of moving bodies which employs a modification of the theory of space and time. Light Quanta, March 1905. As Einstein noted to Habicht, it was the first of these 1905 papers, not the famous final one expounding a theory of relativity, that deserved the designation revolutionary. Indeed, it may contain the most revolutionary development in the history of physics. Its suggestion that light comes not just in waves but in tiny packets, quanta of light that were later dubbed photons, spirits us into strange scientific mists that are far murkier, indeed more spooky, than even the weirdest aspects of the theory of relativity. Einstein recognized this in the slightly odd title he gave to the paper, which he submitted on March 17, 1905, to the Annalen der Physik. On a heuristic point of view concerning the production and transformation of light. Heuristic? It means a hypothesis that serves as a guide and gives direction in solving a problem, but is not considered proven. From this first sentence he ever published about quantum theory until his last such sentence, which came in a paper exactly 50 years later, just before he died, Einstein regarded the concept of the quanta and all of its unsettling implications as heuristic at best, provisional and incomplete, and not fully compatible with his own intimations of underlying reality. At the heart of Einstein's paper were questions that were bedeviling physics at the turn of the century, and in fact have done so from the time of the ancient Greeks until today. Is the universe made up of particles, such as atoms and electrons? Or is it an unbroken continuum, as a gravitational or electromagnetic field seems to be? And if both methods of describing things are valid at times, what happens when they intersect? Since the 1860s, scientists had been exploring just such a point of intersection by analyzing what was called black body radiation. As anyone who has played with a kiln or a gas burner knows, the glow from a material such as iron changes color as it heats up. First, it appears to radiate mainly red light. As it gets hotter, it glows more orange, and then white, and then blue. To study this radiation, Gustav Kirchhoff and others devised a closed metal container with a tiny hole to let a little light escape. Then they drew a graph of the intensity of each wavelength when the device reached equilibrium at a certain temperature. No matter what the material or shape of the container's walls, the results were the same. The shape of the graphs depended only on the temperature. There was, alas, a problem. No one could fully account for the basis of the mathematical formula that would produce the hill-like shape of these graphs. When Kirchhoff died, his professorship at the University of Berlin was given to Max Planck. Born in 1858 into an ancient German family of great scholars, theologians, and lawyers, Planck was many things that Einstein was not. With his pince-nez glasses and meticulous dress, he was very proudly German, somewhat shy, steely in his resolve, conservative by instinct, and formal in his manner. His conservatism made Planck skeptical about the atom and of particle rather than wave and continuous field theories in general. In one of our planet's little ironies, Planck and Einstein would share the fate of laying the groundwork for quantum mechanics, and then both would flinch when it became clear that it undermined the concepts of strict causality and certainty they both worshipped. In 1900, Planck came up with an equation partly using what he called a fortuitous guess that described the curve of radiation wavelengths at each temperature. In so doing, he accepted that Boltzmann's statistical methods, which he had resisted, were correct after all. But the equation had an odd feature. It required the use of a constant, which was an unexplained tiny quantity that needed to be included for it to come out right. It was soon dubbed Planck's constant, h, and is now known as one of the fundamental constants of nature. At first, Planck had no idea what, if any, physical meaning this mathematical constant had, but then he came up with a theory that he thought applied not to the nature of light itself, but to the action that occurred when the light was absorbed or emitted by a piece of matter. He posited that the surface of anything that was radiating heat and light, such as the walls in a black-body device, contained vibrating molecules or harmonic oscillators like little vibrating springs. These harmonic oscillators could absorb or emit energy only in the form of discrete packets or bundles. These packets or bundles of energy came only in fixed amounts, determined by Planck's constant, rather than being divisible or having a continuous range of values. Planck considered his constant a mere calculational contrivance that explained the process of emitting or absorbing light, but did not apply to the fundamental nature of light itself. Nevertheless, the declaration he made to the Berlin Physical Society in December 1900 was momentous. We therefore regard, and this is the most essential point of the entire calculation, energy to be composed of a very definite number of equal, finite packages. Einstein quickly realized that quantum theory could undermine classical physics. All of this was quite clear to me shortly after the appearance of Planck's fundamental work, he wrote later. All of my attempts to adapt the theoretical foundation of physics to this knowledge failed completely. It was as if the ground had been pulled out from under us, with no firm foundation to be seen anywhere. In addition to the problem of explaining what Planck's constant was really all about, there was another curiosity about radiation that needed to be explained. It was called the photoelectric effect, and it occurs when light shining on a metal surface causes electrons to be knocked loose and emitted. In the letter he wrote to Maritz right after he learned of her pregnancy in May 1901, Einstein enthused over a beautiful piece by Philipp Lenard that explored this topic. Lenard would be one of Einstein's early inspirations, but later one of his most hateful anti-Semitic tormentors. Lenard's experiment found something unexpected. When he increased the frequency of the light, moving from infrared heat and red light up in frequency to violet and ultraviolet, the emitted electrons sped out with much more energy. Then he increased the intensity of the light by using a carbon arc light that could be made brighter by a factor of 1,000. The brighter, more intense light had a lot more energy, so it seemed logical that the electrons emitted would have more energy and speed away faster. But that did not occur. More intense light produced more electrons, but the energy of each remained the same. This was something that the wave theory of light did not explain. Einstein had been pondering the work of Planck and Lenard for 4 years. In his final paper of 1904 on the general molecular theory of heat, he discussed how the average energy of a system of molecules fluctuates. He then applied this to a volume filled with radiation and found that experimental results were comparable. He was thus primed, so it seems, to form a theory that the radiation field was made up of quanta. In his 1905 light quanta paper, published a year later, he did just that. He took the mathematical quirk that Planck had discovered, interpreted it literally, related it to Lenard's photoelectric results, and analyzed light as if it really was made up of point-like particles. Light quanta, he called them, rather than being a continuous wave. Einstein began his paper by describing the great distinction between theories based on particles and theories that involve continuous functions. There exists a profound formal difference between the theories that physicists have formed about gases and other ponderable bodies and Maxwell's theory of electromagnetic processes in so-called empty space, he noted. While we consider the state of a body to be completely determined by the positions and velocities of a very large yet finite number of atoms and electrons, we make use of continuous spatial functions to describe the electromagnetic state of a given volume. Before he made his case for a particle theory of light, he emphasized that this would not make it necessary to scrap the wave theory, which would continue to be useful as well. The wave theory of light, which operates with continuous spatial functions, has worked well in the representation of purely optical phenomena and will probably never be replaced by another theory. His way of accommodating both a wave theory and a particle theory was to suggest in a heuristic way that our observation of waves involves statistical averages of the positions of what could be countless particles. It should be kept in mind, he said, that the optical observations refer to time averages rather than instantaneous values. Then came what may be the most revolutionary sentence that Einstein ever wrote. It suggests that light is made up of discrete particles or packets of energy. According to the assumption to be considered here, when a light ray is propagated from a point, the energy is not continuously distributed over an increasing space, but consists of a finite number of energy quanta which are localized at points in space and which can be produced and absorbed only as complete units. Einstein explored this hypothesis by determining whether a volume of black-body radiation, which he was now assuming consisted of discrete quanta, might in fact behave like a volume of gas, which he knew consisted of discrete particles. First, he looked at the formulas that showed how the entropy of a gas changes when its volume changes. Then he compared this to how the entropy of black-body radiation changes as its volume changes. He found that the entropy of the radiation varies with volume according to the same law as the entropy of an ideal gas. This led Einstein to declare that the radiation behaves thermodynamically as if it consisted of mutually independent energy quanta. It also provided a way to calculate the energy of a particle of light at a particular frequency, which turned out to be in accord with what Planck had found. Einstein went on to show how the existence of these light quanta could explain what he graciously called Lenard's pioneering work on the photoelectric effect. If light came in discrete quanta, then the energy of each one was determined simply by the frequency of the light multiplied by Planck's constant. If we assume, Einstein suggested, that a light quantum transfers its entire energy to a single electron, then it follows that light of a higher frequency would cause the electrons to emit with more energy. On the other hand, increasing the intensity of the light, but not the frequency, would simply mean that more electrons would be emitted, but the energy of each would be the same. That was precisely what Lennart had found. By blowing on Planck's embers, Einstein had turned them into a flame that would consume classical physics. What precisely did Einstein produce that made his 1905 paper a discontinuous, one is tempted to say quantum, leap beyond the work of Planck? Einstein considered the light quantum to be a feature of reality, a perplexing, pesky, mysterious, and sometimes maddening quirk in the cosmos. For him, these quanta of energy, which in 1926 were named photons, existed even when light was moving through a vacuum. Einstein's theory produced a law of the photoelectric effect that was experimentally testable. The energy of emitted electrons would depend on the frequency of the light according to a simple mathematical formula involving Planck's constant. The formula was subsequently shown to be correct. Einstein would increasingly find the eerie implications of the quantum and of the wave-particle duality of light to be deeply unsettling. In a letter he wrote near the end of his life to his dear friend Michele Besso, after quantum mechanics had been accepted by almost every living physicist, Einstein would lament, "All these 50 years of pondering have not brought me any closer to answering the question, what are light quanta?"